Now we're going to talk about some applications of quadratics. This one has to do with a trajectory of a football that's been kicked. In other words, the path of that football. If you were standing on the sideline and the player kicked it, what would that parabolic path look like as you were watching it whiz through the air? The project you're going to do is going to be a little different. It's not going to be the trajectory of a tennis ball. It's going to be the how far the tennis ball falls and what is the gravity and so on and so forth. So this is a little different, but we're going to start with this. So here we go. An application, a football application of quadratics. So here we have a parabolic path of a punted football. If you kick a ball, it starts low, it goes high, and then it comes back down, and it's in the path of a parabola. And here we go. We got this, I know you love my drawings. This probably looks like a guy with an afro, but that's really a football helmet. And so this is a football player, and he is punting a football. And there's the trajectory of that football. And we got this other guy here who's trying to block that football. The place where the guy punts the football is not on the ground. It's going to be, he's kind of like, this is like a drop punt. So that's to be the point of impact. And this is that horizontal distance is the distance down the field. In other words, how far would the ball travel if the little guy in yellow wasn't able to intercept it. Okay. So this is what the trajectory looks like if we kind of put it on a rough graph. And notice that this is not starting, whoops, wrong thing to do. Okay, here we go, stop one more time. This is not starting from zero, okay? It's starting from above the ground. But anyhow, this is the formula for this particular trajectory. Now, where did we get this? Well, we just got it somewhere. Somebody told us. We didn't go back. We didn't go out and figure it out. We're just going to accept that this is the way that it is. And notice that because the leading coefficient is a negative, we have a downward opening parabola. Okay. So we've got the beginning is a little bit above the ground, and actually it's 2 feet above the ground because we have our C is equal to 2. It's going to hit the ground at some time out in space somewhere, and that is going to be, our distance there will be x. Okay, and our height above the ground is going to be y. So the first question we're going to ask is, what is the maximum height of the punt and how far from the point of contact does it occur? Well, that's going to be the height. If we look at the axis of symmetry and the vertex, the y value of that vertex is going to be our height, our maximum height above the ground, and our distance from the beginning to that axis of symmetry is going to be at what point on the ground that happens. So we have x, and our vertex is xy. So now, once again, let's get this back over here. We've got our formula. And now the second thing we want to ask is, how far must the blocker reach up to block the ball if he is 6 feet from the point of impact? He's not 6 feet tall necessarily. He is 6 feet away from where the guy kicked the ball. That's along the x-axis. So if this is 6 feet, we need to find out how tall that's going to be. So that if x is 6, then the height is going to be f of 6. Remember that. Okay, we have our little graph and all this stuff all over again. And now we have, if the ball is not blocked, how far down the field will it land? Let's say the blocker tripped and fell and missed it entirely, and so the ball just follows the trajectory. Where will it land down here? How far out will it land? That's the next question we want to ask. In other words, what is x equal when y equals 0? Because remember, this is, when it hits the ground, it is 0 feet above the ground. When it's on the ground, it's 0 feet above the ground. So y is equal to 0, and we can solve that. Okay, so now we have our formula, or our equation. And the vertex, the maximum height and how far, that's what we're looking for. Well, to find the vertex, we're going to find the x value, which is how far down the field would be, which is minus b over 2a. And that is going to be 59 feet. And you can go ahead and do those calculations. I expect you to be able to do this. I'm doing it for you right now, but you're going to have to calculate it on your own. And this is a calculator problem because it's a real life problem. I wouldn't want you to keep this in a radical form. I want you to have it in actual feet, probably to 1/10 of a foot. And in our case, we can even round it to 1 foot. So anyhow, so it's going to be, x is going to be 59 feet at the highest point. And that would be downfield. So he kicks the ball, and it's going to reach its highest point 59 feet downfield from him. Okay, so now if we plug 59 in for x, we'll find out how far above the ground it was, which is 36.81 feet, almost 37 feet. There we go, just said that. So it's going to be 5936.81 approximately, and that's what our vertex is. That's the highest point. Okay, now we're going to draw this in here again, and we're going to say, well, if x equals 6, and we plug 6 in for x, then we're going to find that the height, which is going to be right here, whoops, it's going to be right here, that height is going to be 8.72 feet, or about 9 feet. So 6 feet from where the guy kicked it 1 foot off the ground, the ball is going to be about 9 feet off the ground. Now that did the guy block it or not? I don't know. Did he get up at least a little less than 9 feet when he jumped to get it? We don't know. Okay, 8.72 feet is that. So now let's find where the ball will hit the ground. The ball will hit the ground when y equals 0. So if you plug in 0 using, I'm sorry, we're not plugging 0. Forgive me. We are finding the roots. So we're solving our quadratic equation for y equals 0. And when we do that, I'm just giving you what the equation is. You're going to have to use the quadratic formula, otherwise you'll drive yourself crazy. And because it's a real life situation, we need to use this. So we get y equals minus 1.7. Well, we can't be minus 1.7 down the field in a real world situation, but we can be about 120 feet. So we're going to discount the minus 1.7. It's not that it doesn't exist. It just doesn't exist in the first quadrant, because minus 1.7 is for x is in the minus 1.70 is in the second quadrant. So it really does have some bearing on a pure mathematical parabola, but we can't do minus 1.7. So we know it's going to be about 120 feet downfield if it's not blocked. Okay, the minus 1.7 comes over here, where the graph actually goes beyond, or goes left of where the 2 foot place where the guy kicked it. So technically it went back, and it would have been at minus 1.7. But once again, we're looking at the real world situation, which starts at 0. Okay, so we want to graph this, and we're going to do a sketch of the graph. And here's what we know. We know that the y-intercept is 2, so it's going to start at 2. We know that it goes out about 120 feet before it hits the ground if it wasn't blocked. We also know that our vertex is 59 and about 37. 59 is almost 60, which makes it 120. So with our rounding, we're okay. And we also know that the distance from the origin to the vertex is, or the not the vertex, but the axis of symmetry is about the same, or is exactly the same as the axis of symmetry to where it hits the ground. And because of our rounding, we're okay with this. So there is our graph. And once again, if we continue the graph beyond 0, we're going to wind up with x equals minus 1.7. Go ahead and do your checkpoint number 5. We will be starting on our project next class period, and the project will count as a test grade. It's going to be on vertical motion, and there's a plane going over, so I'm sure you're able to hear that since everything picks up on this. And have a great day, my friends. I'll talk to you later. Bye.